Hi, I'm Matthew Barroso. I'm a rising fourth year physics major, CS minor at Georgia Tech. This summer I was a part of the Neutrino REU program, and I have been working with Dr. Mariani and Dr. Jiang on final state interaction, or FSI analysis. So to understand what I have been working on, I first need to introduce to what has led up to this. First, what we are trying to do is study neutrinos, which are elementary particles, part of the standard model of particle physics. The standard model is a model of physics meant to be a description of everything in physics, and it does a pretty good job except for the small detail that it completely misses explaining gravity, but that's another story. The standard model gives a list of elementary particles, that is, particles that aren't made of anything else, that exist in nature, such as our friend the electron, here. One of these particles are neutrinos, which can exist in three different so-called flavors, and it can oscillate between these three flavors. We would like to study this oscillation. This oscillation is dependent upon the neutrino's energy. Thus, we would need a good way of measuring the neutrino's energy to study its oscillation. The problem is neutrinos are extremely hard to observe. So to study them, we would like to conduct a so-called neutrino scattering experiment. That is, we would like to have neutrinos run into atomic nuclei and look at the effects of the collision and use conservation laws to determine what the neutrino looked like. The problem is we first need to have a very good idea of what the neutrino interacting with a nucleon would look like. To do this, we study something technologically easier, that is electron scattering, which is the same idea but with electrons instead. Here's a diagram of the interaction we're looking at. So my work this summer was to understand the final state interaction, which is the idea that the incoming particle might interact with inside the nucleus before exiting, as pictured here. So previous studies on this did not account for FSI, and we worked on implementing this into our model. And here is an example of the predicted cross-section by the model, this blue curve, and here is the actual data, this red curve. Clearly, the model isn't exactly correct in its prediction, so to fix our model, the idea is that the cross-section predicted without FSI can be scaled by some factor to get the cross-section with FSI. To help fix our model, I first used some Fortran code provided by Dr. Carlotta Giusti to calculate the cross-section for many different orbitals over a bunch of energy ranges. I then used a C program by Dr. Jiang to take the output of the Fortran code and find this factor I mentioned by scraping through the output. This plot is the data used to find the factor, this factor. And finally, I used another C program to reweight the model using the factors from the other C program. Finally, after the reweight, as you can see, this purple curve, our model much more closely matches reality, which is this red curve. And again, here is the old data, or the old model. As you can see, it's not perfect, but it's much better than before. So future research in this might include uh, adding other factors to the model that might bring it closer to actual data. So that is all I have. Thank you for listening. Have a good day. Bye bye.